In this video, we're going to describe periodic trends as a result of electron configurations in atoms. The two trends we're going to look at are ionization energy and size trends in both atoms and ions. The first thing we need to understand when describing the size of atoms and ions is this idea of effective nuclear charge. Effective nuclear charge is essentially how much of the nucleus any given electron feels. The electrons that are closest to the nucleus feel the greatest effective nuclear charge, and the electrons furthest away feel the smallest amount. And the effective nuclear charge is what dictates how big or small the ionization energy is, as well as how free the electron is available to move away from the nucleus. We can calculate the effective nuclear charge based off of the total number of protons an atom has, and we subtract that from the screening electrons. And the screening electrons are always the number of electrons that are present in the previous row's noble gas. In order to better visualize and understand how the concept of effective nuclear charge works, think of a concert. You've got the nucleus, which is at the center of the atom, or the concert where the concert performers. So let's just say here we've got a positive charge, and we've got a neutron and another positive charge. And so this is our stage. Well, where's the best seat in the house? Where do you have the greatest amount of interaction with the nucleus? Well, when you're in the first row or the 1s orbital. So the electrons here feel the greatest amount of nuclear charge. And so they have the best view. They're held on the tightest. Where's the next best seat? Well, it's the second row, or the 2s orbital. The 2s orbital has a pretty good view of the nucleus, but not as good as the 1s orbital. The 1s orbital, when we calculate the effective nuclear charge in this fictitious atom, and let's just say there's a grand total of 25 positive charges here. I just didn't draw them out. So we would say 25 protons, and in the 1s orbital there are no screening, so the effective nuclear charge for these two electrons here is plus 25. They feel the force of all 25 protons. As a result, those electrons are drawn incredibly close to our stage, or the nucleus. If we continue to add electrons to the second row, we'll put a third electron right there. Well, now all of a sudden the effective nuclear charge is the 25 protons minus, well, we've got someone blocking our view here, these guys. So we have two screening electrons, meaning that they feel only 23 of the 25 protons. They're not held as tightly. And as a result, they're free to move further away from the nucleus than the 1s. So the 2s is further away because the effective nuclear charge isn't as great. So what we see in terms of atomic radii, which is measured by taking the distance between two nucleuses, is that the size of atoms actually shrinks as we move from left to right. And the reason for that is the number of protons increases as we move from left to right on the periodic table, so the effective nuclear charge increases as you move left to right. All column 1 elements have a positive 1 effective nuclear charge on their outermost electron. Column 2 plus 2. Column 3A plus 3. Column 4A plus 4, and so on and so forth. As a result, the size of an atom shrinks as you move from left to right. So big atom on the left, small atom on the right. However, as we move down the periodic table, we're increasing principal quantum numbers. We're adding more levels to our apartment building. The result of that is we see an increase in the radius. So if you want to try and memorize the prediction for size, size increases moving top down and from right to left. Now, ions are slightly different, and it depends upon whether or not we're talking about a cation or an anion. Cations, the size decreases compared to that of the element because there's now more positive charges than there are electrons. So as a result, all the electrons are held together slightly tighter. On the other hand, anions have extra electrons. As a result of that, we see the extra electron causes the size of the ion to expand because there aren't as many positive charges as negative. There's more negative charges, there's more repulsive force surrounding the nucleus, and so things have to spread out a little bit in order to accommodate the extra electrons. So the outermost electron is removed for cations, and the repulsive forces it starts to go down, and the attractive force between the nucleus and the remaining electrons causes things to shrink. Anions, it's just the opposite. They have to expand to accommodate the extra electron. The effective nuclear charge isn't strong enough to hold on to the electrons quite as well. And just like we saw in the periodic table, ions increase in size as you move from top down, and cations, the more positively charged they become, the smaller they get. Anions, the more negatively charged they become, the bigger they get. So these are a couple of trends that you're going to want to commit to memory. And you should be able to compare sizes between elements on the same row or on different columns when you are trying to organize size of atoms and ions. Now, there's a particular way to organize elements which have the same number of electrons, and this is known as an isoelectric series. So an isoelectric series is a set of electrons several ions have. So, for example, O2 minus, F minus, these both have the same total number of electrons. So when two ions are isoelectric to each other, they have the same number of electrons. So when you're comparing isoelectric elements, the one with the most negative charge is the biggest. The one with the most positive charge is the smallest. Let's shift gears now and talk about ionization energy. Ionization energy is the energy required to remove an electron from the outermost orbital of an atom. And so the first ionization energy is the energy required to remove the first electron. The second ionization energy is the energy required to remove the second electron after the first electron has already been removed. What we see in terms of ionization energies is that ionization energy generally increases as we move from left to right. It becomes progressively more difficult to take electrons out of an orbital because the effective nuclear charge is increasing as we move from left to right. As we move from the top down on the periodic table, things become slightly easier. And that's because as you move down the periodic table, the outermost electrons are further away from the nucleus. Now, all of these ionization energies you see here, for example, for sodium, you can see the first ionization energy is 496. And if we move over to magnesium, which is immediately to the right of it on the periodic table, we see that the amount of energy increases. And that makes sense. Magnesium has a +2 effective nuclear charge, sodium has +1. But what about removing 2 electrons from sodium? Is that possible? Well, it is possible, but it never happens in a chemical reaction. If we see sodium with a +2 charge, it's because we're basically putting it in some sort of plasma environment where electrons can be stripped, and so we'll never ever see a sodium with a +2 charge in any of the chemistry we do. Or for that matter, unless you go into solar chemistry, you'll never see a sodium with a +2 charge. But we can measure how much energy it takes to remove the second electron, and you can see going from 1 electron removed to 2 electrons removed causes a factor of 10 jump in the amount of energy. Why is this? Well, sodium has 1 electron in its outer valence, and so the first electron is held on weakly and it's free to fall off or be stolen away. The second electron, now that's from the previous row's noble gas, and so we're talking about removing a core electron. Core electrons are simply electrons that are in the previous row or rows that come before the particular row you're on the periodic table. Hopefully that makes sense. So removing core electrons costs an astronomical amount of energy, and we never see core electrons come off during the course of a chemical reaction. So what are our trends? We have ionization energy as we move from left to right increasing, and ionization energy increases as we move from the bottom to the top.